Imagine a cosmic fountain, a place in the universe where matter and energy are spewed out into the cosmos, rather than being sucked in. This isn't science fiction, it's the mind-bending concept of a white hole. If black holes are the universe's vacuum cleaners, white holes are its fire hoses, blasting out matter and energy at incredible speeds. But do they really exist? And if they do, what secrets could they unlock about the very fabric of our universe? Stick around, because we're about to dive into one of the most intriguing and mysterious phenomena in astrophysics. White hole definition, theoretical counterpart to black holes. White holes are fascinating theoretical objects that are often described as the opposite of black holes. They are regions of spacetime where matter and light can only escape, never enter. This is in stark contrast to black holes, which pull in everything that comes too close, including light. The concept of white holes emerged from the mathematical solutions to the equations of general relativity, the same theory that describes black holes. Just as black holes represent a singularity, or a point of infinite density, from which nothing can escape, white holes represent a singularity from which matter and energy can only exit. The idea of a white hole is intriguing because it challenges our understanding of the universe. While black holes are well-documented and observed phenomena, white holes remain purely theoretical. They are predicted by the same equations that describe black holes, but no direct evidence of white holes has been found. This lack of evidence doesn't mean they don't exist, but it does mean that their existence is still a topic of debate and speculation among scientists. Some theories suggest that white holes could be the other end of a black hole, connected through a wormhole, a hypothetical tunnel through spacetime. One of the most compelling aspects of white holes is their potential to explain some of the mysteries of the universe. For instance, they could be a source of new matter and energy, constantly spewing out material into the cosmos. This could have implications for the formation of galaxies and stars, as well as the overall structure of the universe. However, without concrete evidence, these ideas remain speculative. Scientists continue to explore the possibilities, using advanced theories and models to understand whether white holes could exist and, if so, what role they might play in the cosmos. Until then, white holes remain a captivating concept, bridging the gap between theoretical physics and our imagination. Relativity predictions. Why equations allow them. Einstein's theory of general relativity is a set of equations that describe how gravity works. These equations are incredibly powerful and can predict some truly bizarre phenomena. One of these is the existence of white holes. Now, you might have heard of black holes, which are regions in space where gravity is so strong that nothing, not even light, can escape. White holes are like the opposite of black holes. They are regions where matter and light can only escape, not enter. It's as if a black hole has been turned inside out. The equations of general relativity allow for the existence of white holes because they are mathematically consistent with the idea of a time-reversed black hole. In other words, if you take the equations that describe a black hole and reverse the direction of time, you get the equations that describe a white hole. This is a fascinating example of how the laws of physics can be symmetric in time. It's like watching a movie of a black hole in action and then playing it backward. The equations don't care which direction time is moving. They just describe the relationships between different physical quantities. However, it's important to note that while the equations allow for white holes, there is no direct evidence that they exist in nature. This is a common theme in physics. The equations can predict many things that we might not observe in everyday life. For example, the equations of quantum mechanics allow for the existence of virtual particles, which are particles that pop in and out of existence in a vacuum. We can't see these particles directly, but we can observe their effects. Similarly, while we might not have observed white holes directly, their existence is a fascinating prediction of the equations of general relativity. Another way to think about this is to consider the concept of singularities. A singularity is a point in space where the laws of physics as we know them break down. Black holes are thought to have singularities at their centers, where matter is crushed to an infinite density. White holes would also have singularities, but in their case, it would be a point of infinite density from which matter is expelled. The equations of general relativity allow for these singularities, but they also suggest that our understanding of physics might need to be expanded to fully understand what happens at these points. It's a reminder that while the equations can predict many things, there's still much we don't know about the universe. Ejecting matter instead of absorbing. Basic model. White holes are theoretical cosmic objects that are the reverse of black holes. Instead of pulling in matter and light, they eject it. This concept is based on the mathematical solutions to Einstein's equations of general relativity. The idea is that while black holes have an event horizon from which nothing can escape, white holes have an event horizon from which nothing can enter. Think of it like a cosmic fountain, constantly spewing out matter and energy. The basic model of a white hole involves a singularity, a point of infinite density, but instead of pulling everything in, it pushes everything out. This is the opposite behavior of a black hole. The matter and energy ejected by a white hole come from its singularity. It's like a reverse waterfall, where instead of water flowing down, it's constantly gushing up. This process is perpetual, meaning it doesn't run out of material to eject. One of the key differences between black holes and white holes is the direction of time. In a black hole, time moves inward toward the singularity. In a white hole, time moves outward, away from the singularity. This means that any matter or energy that enters a white hole from the past would be ejected into the future. It's a bit like a cosmic time machine, but instead of sending things back in time, it sends them forward. The concept of white holes is still purely theoretical. There's no direct evidence that they exist. However, they are a fascinating area of study in theoretical physics. Scientists explore them to better understand the nature of spacetime, the fabric of the universe. The idea of a white hole challenges our understanding of causality and the arrow of time. It's a reminder that the universe is full of mysteries waiting to be uncovered. Why no white hole has been observed? White holes are theoretical regions in spacetime that are the opposite of black holes. While black holes pull in matter and energy, white holes are thought to eject them. Despite their intriguing nature, no white hole has ever been observed. There are several reasons for this. One major reason is that white holes, if they exist, would be incredibly short-lived. According to theoretical models, a white hole would explode immediately after forming, releasing all the matter and energy it contains. This makes them extremely difficult to detect. Additionally, the conditions necessary for a white hole to form are so extreme that they are unlikely to occur naturally. Most theories suggest that white holes would only form in the earliest moments of the universe or under conditions that are impossible to replicate today. Another factor is the immense distances involved in space. The universe is vast, and even if white holes exist, they could be so far away that our current technology cannot detect them. The signals they emit, if any, would be too faint or distorted to be picked up by our instruments. Moreover, white holes might not emit any detectable radiation or particles, making them invisible to our telescopes and other observational tools. Furthermore, the theoretical framework for white holes is not as well developed as that for black holes. While black holes are well studied and their existence is supported by a wealth of observational evidence, white holes remain purely speculative. Scientists have not yet found a way to test the existence of white holes directly. Until more concrete evidence or a robust theoretical model emerges, the observation of white holes will remain elusive. Connection to wormholes and spacetime structures. White holes, the theoretical opposites of black holes, are regions of spacetime where matter and light can only escape, not enter. Their connection to wormholes and spacetime structures is a fascinating area of study in theoretical physics. Wormholes, hypothetical tunnels through spacetime, could potentially connect a white hole to a black hole, creating a bridge across the universe. This idea is based on the Einstein-Rosen bridges, solutions to the equations of general relativity that describe such connections. If a white hole were to exist at one end of a wormhole, it could be spitting out matter and energy that was swallowed by a black hole at the other end. This concept, however, remains purely speculative, as wormholes and white holes have not been observed in nature. The structure of spacetime around a white hole is equally intriguing. Just as black holes warp spacetime, causing extreme gravitational effects, white holes are thought to do the same but in reverse. The region around a white hole, known as the event horizon, would be a boundary from which nothing can enter. Inside this horizon, the spacetime curvature would be so intense that it could potentially create a path to another universe or a different part of our own. This idea ties into the broader concept of a multiverse, where our universe is just one of many, possibly connected by wormholes and white holes. One of the most compelling aspects of white holes is their potential to explain certain cosmic phenomena. For instance, some scientists have theorized that the Big Bang itself could have been a white hole event, with matter and energy bursting out into the void to create our universe. This idea, while controversial, highlights the deep connection between white holes, spacetime structures, and the fundamental nature of the cosmos. It also underscores the need for further research and observation to understand these enigmatic objects better. In practical terms, the study of white holes and their connection to wormholes and spacetime structures could revolutionize our understanding of the universe. It could lead to new theories about the nature of gravity, the fabric of spacetime, and the ultimate fate of matter and energy. While these ideas are still in the realm of theoretical physics, they offer a glimpse into the profound mysteries that lie at the heart of the cosmos. The journey to unravel these mysteries is ongoing, driven by curiosity and the relentless pursuit of knowledge. Theory that Big Bang was a white hole event. White holes are theoretical regions in spacetime that function in the opposite way to black holes. Instead of pulling matter in, they expel it. This concept arises from the mathematical solutions to the equations of general relativity, which describe black holes. If you reverse the direction of time in these solutions, you get a white hole. Unlike black holes, which are well documented and observed, white holes remain purely theoretical. No direct evidence of white holes exists, making them a fascinating yet speculative topic in astrophysics. The idea that the Big Bang could have been a white hole event is intriguing. In this scenario, the universe began as a white hole, violently expelling matter and energy that eventually formed the cosmos we see today. This theory suggests that the Big Bang was not a singularity but rather the result of a white hole's ejection of matter. It's a compelling alternative to the traditional understanding of the Big Bang, which typically describes it as a singularity from which space and time emerged. The white hole theory offers a different perspective, one that ties the origin of the universe to the behavior of these hypothetical objects. Proponents of this theory argue that a white hole could explain certain observed properties of the universe. For instance, the uniform distribution of matter and energy across the cosmos might be a result of a white hole's expulsion. Additionally, the absence of a central singularity in this model avoids some of the paradoxes associated with the traditional Big Bang theory. However, this remains a speculative idea. Without direct evidence, it's challenging to confirm or refute the white hole origin of the universe. The theory serves as a thought-provoking alternative, encouraging further exploration and debate in the field of cosmology. The concept of a white hole as the origin of the universe also raises questions about the nature of time and causality. If the Big Bang was a white hole event, it might imply that time itself has a direction dictated by the white hole's behavior. This challenges the conventional view of time as a linear progression from the Big Bang to the present. Instead, it suggests a more complex relationship between time and the fundamental forces of the universe. While these ideas are speculative, they highlight the potential for white holes to reshape our understanding of cosmology. Problems and criticism from physicists. White holes, the theoretical opposites of black holes, have sparked considerable debate and criticism within the physics community. One of the primary issues is their lack of observational evidence. Unlike black holes, which have been detected and studied extensively, white holes remain purely hypothetical. This absence of empirical data makes it challenging to validate their existence or the theories surrounding them. Physicists often point out that without concrete evidence, white holes risk being speculative constructs rather than scientifically grounded phenomena. Another significant criticism revolves around the theoretical inconsistencies associated with white holes. According to general relativity, a white hole would be a region of spacetime from which matter and light can only escape, never enter. This idea introduces several paradoxes and contradictions. For instance, the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease over time, seems to be violated by the nature of white holes. They would essentially be sources of matter and energy, which contradicts the known behavior of the universe. These inconsistencies make many physicists skeptical about the viability of white holes as real astrophysical objects. Additionally, the concept of white holes raises questions about causality and time. If white holes are indeed the time-reversed counterparts of black holes, they would imply that matter and energy are being ejected from a point in the past. This idea challenges our understanding of cause and effect, as it suggests that events could have effects that precede their causes. Such a notion is not only counterintuitive but also difficult to reconcile with the established principles of physics. Critics argue that until these fundamental issues are resolved, white holes should be treated with caution and viewed more as mathematical curiosities than as physical realities. Furthermore, the theoretical framework supporting white holes often relies on extreme and perhaps unrealistic conditions. For example, the formation of a white hole would require a reversal of the gravitational collapse that leads to black holes. This reversal would need an incredibly specific and unlikely set of initial conditions. Many physicists argue that such conditions are not only improbable but also not supported by any known physical processes. This skepticism is compounded by the fact that white holes do not fit neatly into existing models of cosmic evolution and structure formation. Until more robust theoretical and observational support is found, white holes will likely remain on the fringes of mainstream astrophysics. Future detection possibilities. Detecting white holes is a challenge due to their elusive nature and the fact that they haven't been directly observed yet. However, scientists have some ideas on how to spot these cosmic oddities in the future. One promising avenue is through their unique radiation signatures. White holes are theorized to emit intense radiation, potentially detectable by advanced telescopes. This radiation would be different from that of stars or black holes, offering a distinctive signature. Researchers are developing new instruments and techniques to capture and analyze such signals. Another approach involves studying the behavior of matter around potential white holes. Unlike black holes, which pull in matter, white holes are thought to eject it. This could create observable patterns in space, such as jets of material or unusual energy distributions. Telescopes equipped with high-resolution imaging could detect these patterns, providing indirect evidence of white holes. Additionally, the gravitational effects of white holes might be observable. Just as black holes warp spacetime, white holes could create similar distortions, detectable through precise measurements of gravitational waves or the motion of nearby stars. Future space missions could also play a crucial role. Proposed missions to study black holes and other exotic objects might serendipitously detect white holes. For instance, telescopes designed to observe the event horizon of black holes could be repurposed to search for the opposite phenomenon. Moreover, advancements in quantum technology might enable the detection of the unique quantum signatures of white holes. Quantum sensors could measure the subtle changes in the fabric of spacetime caused by these enigmatic objects. Collaborative efforts among scientists worldwide are essential for progress. By sharing data and resources, researchers can pool their knowledge to develop more effective detection methods. International space agencies and observatories are already working together on projects like the Event Horizon Telescope, which could be adapted for white hole detection. As technology advances, the likelihood of detecting white holes increases, bringing us closer to understanding these mysterious cosmic entities. Alright, let's wrap this up. So, to sum it all up, white holes are like the cosmic opposites of black holes. Instead of sucking everything in, they're theorized to spit stuff out. They're rare, mysterious, and we've never actually seen one, but the math suggests they could exist. They might be born from the death of a black hole, or maybe they've been here since the beginning of the universe. Either way, they're a fascinating what-if in the grand story of space. Now, first know what you're thinking. This is all pretty mind-blowing stuff. And you're right. The universe is an incredible place, full of wonders we are only just beginning to understand. If you're as curious as first am, make sure to hit that subscribe button and smash the bell icon. That way, you won't miss out on our next adventure into the unknown. And who knows? Maybe one day, we'll have news about an actual white hole sighting. Wouldn't that be something? Until then, keep looking up at the stars and wondering. After all, every great discovery starts with a question. See you next time, Space Cadets.